We have with us Eric Jang, VP of AI at 1X. Thanks, Eric, for having me here at your new Palo Alto office, and thanks for being my very first guest on the Humanoid Hub.
Welcome to the 1X office, Devang. It's a huge honor that you're doing the face reveal with us as the first interview.
So 1X was founded in Norway. It was established there, and then you opened your presence here in the Bay Area with the Sunnyvale office, and now you've moved to Palo Alto. What has inspired that move, and how is the team adjusting to the new office?
Yeah, so we're moving to a much larger office now that has the hardware, the operations, the AI team, the software team all under one roof. And the main reason for this is that the team has grown quite a lot, and we need to move as fast as possible. So by putting everyone in the same building, we can execute quickly.
That's awesome. So while all the other humanoid players are tackling more structured industrial applications, why has 1X decided to go for the hardest challenge in humanoid robotics, which is the home, uh, which is challenging not just in terms of hardware safety, but also robotics intelligence?
Yeah. So going to the home plays to 1X's strengths as well as also our vision of what we think that the sort of general intelligence of the future really needs to be. So on one hand, we have the hardware strategy we've been building for the last decade, which is very compliant, safe, tendon-driven actuation, and this allows us to have much more lightweight and safe robots that can be around people and be in these environments where you can make unplanned contact, and those aren't going to be inevitable. And that's always been a kind of core part of the DNA of how we feel like robots that work around people are going to be like. So that's a natural fit for deploying in homes. The second piece is that we are going to become a AGI company, not just a robot company. And in order to do this, you need to gather very diverse data in all kinds of environments. We don't get that kind of diversity from repeating a single task in a factory. You want to have as wide of a data distribution as possible with as many tasks as possible. And so you get to see that kind of unstructured diversity in homes. So while it is an extremely challenging environment to deploy autonomy in, of course, generalization is really important here. It is also the ultimate treasure chest of data that we want to gather. And so we think that it's worth to try this problem first.
So the 1X AI team has made some major announcements in the past 1 week. So let's start with talking about Redwood AI, which is your flagship vision language action model. What is your approach to building it, and what's behind the decision of keeping it compact relative to the some of the other models out there?
Of course, yeah. So there's lots of generalist VLAs coming out these days, and our latest one is called Redwood. Redwood is a VLA that can control the entire body of Neo. So this is the lower body, the arms, the hands, the neck, all together at once. To our knowledge, we're one of the first humanoid companies to really put it all together in this kind of whole body way. And this is because we're really focused on chores in the home. We want to be able to, pick up your laundry and carry it over to the laundry machine and all within one model. Our emphasis was really on this kind of whole body control aspect because that kind of proves to us that it works really well with our hardware, which is also very good at doing compliant things like grabbing a door and pulling it open. So we wanted with our AI strategy to kind of really prove out the utility of our hardware combined with our AI. So that's the focus. It is a language controlled model, so we can pass in language into the model and it predicts all the different things.
Right. So many robotic stacks decouple the high level vision from the low level reflex control so that reflexes can run at a much higher frequency.
Mm-hmm.
But what's behind your decision to keep the high level vision and the actions within the same pass, which runs at five hertz?
Yeah, so Redwood is not a high-level reasoner yet. It doesn't do kind of high-level planning at the moment.
I see.
And so that's something that we're actively extending the next version of Redwood with. But the current version of Redwood that we've announced is really about that kind of whole body control and kind of convince ourselves that it's complete from a sort of task completion perspective. Like it can do the low-level control quickly, and it can generalize to different commands, and you can ask it different things, and it can use the whole body. There's a lot of tasks that you need to do in the home that require the full body, like squatting down to pick up something from the laundry or opening a door and backing up while doing it. And that was kind of the focus here. As we work on other tasks in the home that are more around like planning, we imagine that the model will get bigger to accommodate those tasks. That being said, we did put a lot of effort into making the Redwood model as compact as possible. So we've done experiments with models that were bigger, and we found that what really matters to pack intelligence into a small number of parameters is kind of like training it carefully with these so-called cognitive prediction tasks that we added to the model. And that helped a lot to shrink the model.
So the cognitive tasks or cognitive data is what is that?
There's a few different things that we do. One, think about them as like just auxiliary prediction tasks to reason about the world that ground the representations in, so that the representations kind of really understand the world, right? Maybe think about a prediction task like where's my hand, or where's my hand going to close in the future? What am I looking at in terms of objects, things of that nature.
Right. So how do you see scaling the data labeling for the cognitive heads?
Yeah, it's a good question. We start to see some similar kinds of things being done in other system 1, system 2 neural networks. Like often when you're training like a big VLA, you might co-train it on internet question answering tasks, like visual question answering. And so, of course, like you can imagine something like Gemini Robotics doing this at a very large scale where they pre-train VLA and then they co-train it with actions. What we did was kind of make a miniature version of this where we co-train with these auxiliary perception and cognitive tasks. And then we also co-train them with actions. As we scale them up, maybe it'll look a lot more like what other kind of big labs are doing with these kind of general internet scale question answering tasks, but how exactly we fold it into the model so that it runs efficiently and still has all the intelligence you need to do the task is something that we're figuring out at the moment. I don't necessarily think it's going to be like a gigantic model with a tiny model attached to it.
Okay. Another major update was the reinforcement learning controller for Neo's mobility. Neo is able to walk up and down stairs, run, walk sideways. How is training Neo for practical home task and mobility different from what makes robots like Optimus dance with reinforcement learning controller?
Right. So the motivation for us extending and building on the RL stack, the natural mobility update that we did, was that in order to be useful in the home, the AI or teleop have to be able to maximally utilize Neo to access the space, right? Like most home robots that I know of today cannot climb up the stairs and down the stairs, maybe with the exception of the Spot robot from Boston Dynamics, which is like a quadruped. Right. But I'm not aware of like any home product robot that can go up and down stairs, and that really limits your access to what you can do in the home. And similarly, like if you have a humanoid, most people use humanoids, most labs use humanoids as sort of a bimanual manipulator. They just have it standing in front of a table and they do some stuff in front. But really a humanoid is about accessing everything. So you want to bend down under the table and pick something up off the floor and put it back on the table, or you want to reach high into a shelf and grab something off the shelf on your tippy toes and then bring it down. So the reason why we do humanoids in the first place is because the world is really designed for humans, and of course all humanoid robotics people know this, but their software doesn't necessarily enable their robot to do this. And so what we've done with this RL update is to make the software utilize as much of the power of the hardware as possible. So you mentioned the Optimus dancing. I don't know exactly how they did it, but my guess would be that that, along with other recent demonstrations we've seen from like Unitree and Engine AI, is more about training RL controllers that can track a very specific mocap trajectory very well. And you can see that it dances very well. It's very cool.
Right.
And it follows the trajectory really nicely without falling over. That's really cool because you can make the movements natural, but the step that you need to take after that is to make it controllable. Because if you can replay a single dancing motion, it's not going to be useful in a home because you need to actually steer it to do certain things, right? So what we wanted to do with this update was to combine the naturalness of that kind of technology where you train it to follow mocap references, but also make it just as controllable as sort of the first generation of RL controllers that people train in Sim2Real, where you can kind of steer it around with a joystick or VR or something. So when you marry both of them, then you have something that looks natural and you can actually use it for tasks. And so that was kind of the core contribution of our update.
Question on the onboard GPU that you have on Neo, which is running your models and controller. As you scale up the data, your model is likely to grow. How do you think about growing the capacity of the compute on board, keeping in mind all the trade-offs, let's say 6 months from now or a year from now?
Yeah, it's definitely a really hard problem to pack all these robotics capabilities into a single GPU. We have like safety layers, RL, various perception tasks that we need to do to process sensors, and not to mention the autonomy, high-level planning, potentially like audio generation. So many things need to kind of squeeze into a single GPU and scheduled and not have GPU contention. And so we're definitely really excited about future hardware that lets us run more things, but we have to make it work with the current hardware we have. So we have a dedicated team to basically trying to make our existing resources as efficient as possible.
Cool. So another major update was the 1x world model. What unique challenge does it solve that a physics-based simulator like NVIDIA Isaac Lab doesn't solve?
Yeah, our world model can simulate people. It's got when you see people in the world model, they will actually behave in somewhat human ways. So in some sense, the world model is starting to capture the intelligence of people implicitly through its generation of people pixels. That's one thing that's very hard to put in a traditional rigid body simulator. It's pretty good at cloth and deformables, so it can like move curtains or drop cloth or wipe cloth, and again, an area that's pretty tough in rigid body simulators. And liquids, it understands liquids because liquids are like any other thing that you could simulate in a world model. So these are all objects that you run into very often in a home.
Right.
And so the reason why we're building this world model is that we believe that to do really rigorous evaluation in these unstructured environments like a home, you need like a data-driven simulator, and we don't have the engineering bandwidth to hand author simulations for like all these different homes that we're deployed in. We want a data engine that lets us evaluate on the homes we've deployed in, and that means that we can turn like a log from a real customer deployment into a sort of world model simulation that we can then test counterfactuals on. So that's the reason why we do these world models.
So the world model, is it basically a video generation model?
It is at its core a video generation model, using like a diffusion technique.
Right.
However, one very difficult challenge that we faced in making this world model was making it controllable via actions. So most video generation models are text to video, where you type in a prompt and it generates some video. What we have found was that in the process of converting an existing pre-trained text to video model into our world model, the text to video kind of conditioning layers didn't give us very much, and we actually had to basically retrain the whole thing from scratch to pay attention to actions. And having really, really high quality action data sets was really important to make this work. You don't really get action controllability out of the box from most text to video models. That's not what they are prioritizing, which is kind of an interesting finding. And so we basically had to kind of like mid-train this model from scratch to make it really pay attention to what our robot is doing.
Okay. So you mentioned in your blog that even a world model that is 70% aligned with the real world test would be a useful tool for comparing policy candidates.
Yes.
As the policies mature and the gaps between the policies narrow, how do you make sure the world model keeps improving along with the autonomy?
For sure. That's a really good like open-ended question that we don't know the answer to yet. The way I see the world model is that it can evaluate a huge breadth of things that we cannot possibly hand engineer simulations for. And it gives us this very large coverage that can scale really well with our deployments. We don't know the answer yet as to whether it can give us the precision of a physics-based simulator to like, let's say 99.9% alignment. That seems very high. So at the very least, it gives us breadth. And then we also use physics simulation as a sort of alternate toolkit to evaluate a few scenarios with very high precision. And the hope is that you get, the depth and the breadth with these combination of these two. And then we're going to still scale up the world model so that it becomes more and more accurate. But then as to where that plateaus, it's hard to say, right? If it's a 90% accurate thing, then you can discriminate quite a lot of policies from each other, especially with all the different scenarios you can test in. But if it's 70%, then perhaps you can use that to determine if something is like much worse than before or much better than before. But but nothing really in between.
Yes. And how good does the world model have to be a good synthetic data generation tool?
hmm That's a really exciting direction for us as well. So you can think about a world model as we've designed currently as takes in your current state and your candidate actions, and it tells you what's going to happen in a sort of general physics way. In order to generate data, you want to not feed in actions, but you want to generate actions out, right? And you probably want to prompt it with like what is going to happen. So now the text goes back in, and so there's this kind of interesting blend between text to video models and action to video models, where if you kind of find a way to fuse them together, then maybe you can turn this knob to let you go from like evaluating to data generation. And we're quite confident that we have the data now to generate very high quality video rollouts. So it's probably not too difficult to also generate or diffuse the actions because the image is already so much bigger. And if we can find a way to make really controllable data generation from text, then we have a recipe that can do both evaluation as well as data generation. And we're really excited about doing that. It reminds me a lot of like what Anthropic did with constitutional AI, where instead of pre-training on this big internet data set, they have a model that generates the data and then they train on that. At least maybe that was a few years ago. I don't know what they do today.
Would a very advanced version of a world model pass a Turing test of a physical reality?
Well, yeah, I mean, we start to see people move realistically in the world model now. So you can imagine that like the hallucinated people in the world model get more and more intelligent as we scale it up.
Right.
Not to mention the robot gets more intelligent in the world model, but like you can see like just if you slice out just the behavior of people in the world model and what they do, like there's clearly some intelligent behavior there. And then I'm personally super interested to see like would those people in the world model pass the Turing test at some point? And we see this actually with VO3, right? Like there's people that do some very interesting like interesting generations of people speaking inside of these latest video generation models.
Right.
But with a world model, it's an interactive model in the sense that it can respond it can respond to kind of changes in actions.
Right.
So the way that a Turing test might work is that like the world model responds in a very psychophysically accurate way to interventions by the robot actions.
I see. So beyond robotics, there is a potential maybe in gaming or immersive experiences.
Yeah.
With things like 1x world model.
That's right. Yeah, and we see some startups these days that are trying to basically make controllable world models for games. I think there's a lot of questions around how you like package that thing into a product, but there's definitely intelligence in the things that you see in a world model, especially when they contain animals and people and robots.
You are a big believer in supervised learning. You think it's a super efficient data sponge. Now with reinforcement learning showing good results with manipulation tasks, do you think reinforcement learning can play a complementary role along with supervised learning?
Yeah, absolutely. I still believe that supervised learning is an incredibly efficient way to make use of compute and parameter capacity in a deep neural network, but that does not imply that I don't believe in reinforcement learning, which is improving a system from interaction and feedback.
Right.
Then the question is like, how do you implement reinforcement learning at scale for real world humanoid robots that are deployed in the world, right? Like there's a lot of infrastructure and algorithmic challenges there. Not to mention at very large scales of models, you want to be careful that like you're absorbing intelligence as fast as you possibly can, because if your learning rate is 10x smaller than it should be, then your training run is going to cost 10 times more to make the thing intelligent.
Right.
So at very large scale models and AGI, actually the choice of algorithm that you use to soak up information is very important. It's not like an arbitrary choice. So then the question is, how do you make reinforcement learning as much of a data sponge as possible? And so that's something we're really interested in as well, is to kind of scale up our own intelligence at 1x. We collect lots of data where the autonomy fails, and so there's a big question as how we integrate that in our stack. Our Redwood model actually already trains on both successful and failed rollouts, and not in the sort of strict reinforcement learning way where it does like like an on policy update, but it's more of like it uses the failure data to improve its representations. And that's kind of a first step towards something that's a little bit like RL, and then we'll do more and more.
Yes. So 1X has been testing neo robots in employees' homes. And what has been some of the initial learnings that has maybe informed your decisions in building the AI stack?
Yeah, so one of the lessons we've learned with deploying robots in homes is that reliability is really important, and that's very central to the product experience. I would argue that reliability limits how fast we can actually distribute the robots as a product to homes. Because if, for example, your robots are not super reliable, then you have to keep service techs nearby to fix the robot when it breaks. And so as we scale up, as any company in the space scales up, we're going to have to basically solve reliability in order to solve distribution.
I see. Looking further ahead, to get to fully autonomous humanoid robots that are also truly general purpose, do you think you have all the pieces of the puzzle to scale up the learning, or do you think there are fundamental breakthroughs needed in algorithm or computing to get there?
We certainly don't have every single detail figured out. I would say that our broad stroke strategy of deploy a lot of safe robots in the home and gather the diverse data and use that to trade a general intelligence that understands, homes and people and physical environments really well is something that we think is kind of directionally the right bet. So we think that we have that part figured out. But of course, there's a lot of details like, what is the RL algorithm that you want to use to learn from failures? How do you squeeze all this intelligence into a small compute footprint? How do you ensure safety for a bipedal robot? How do you what is the trade-off between your RL controller and your autonomy controller and the planner? All these things are a little bit fuzzy, and so obviously we don't have all these things figured out. But in broad strokes, we think that it's going to be a deep neural networks trained on lots of diverse data from humans in homes, and then we just spin the data flywheel there.
The humanoid space has an interesting competitive landscape. We have Tesla, Unitree, Figure, and a lot of other startups that are trying to build their own AI. What is 1x's unique advantage in building a foundational AI for humanoid robotics?
Yeah, I think that our main advantage is that we have a hardware strategy that lets us deploy in environments that are very diverse, that we can make unplanned contacts because our hardware is safe. And when you are allowed to make more unplanned contacts, you can now gather more interesting data around maybe trial and error. And from there, you can bootstrap an intelligence that's much more robust because being able to learn from failures is quite important. We see how robust like RL controllers are when they're trained with failures and such. And so I think that that's really important to gather the right data sets. That's like one key piece that we think we're quite ahead on. And then, as for our AI strategy, I think we think about it very comprehensively, starting from this like home first approach. We want to solve chores that make sense in the home. We have a data flywheel that starts with shared autonomy with partial human teleop that we eventually scale up to full autonomy. And we've always been very steadfast in that direction of this kind of building this general AI. So I think we have a lot of clarity in like what we are trying to do and what our technology enables, and that focus helps.
So that's all the questions I had on my list. Is there anything else would you like to share that we haven't touched on yet?
Yeah, maybe a question for you. Like, what is the most extreme out there kind of vision you've seen in the space in the last 6 months? Because there's so many new players and so many things going on in the space now. Like, I think 3 years ago, humanoids was not taken as seriously. Now people take it very seriously. So what is an idea that you've seen out there that is like not taken seriously today?
It is, I think it is being taken seriously, but I would say clone is taking a very unique approach. It still has a long way to go in proving the hardware and the way they are developing the actuators. But I think you can say it's like the idea which is out there,
Mhm.
nobody else is pursuing it. So
Mm,
it's very
mm.
interesting.
Like pneumatic driven robotics.
They have muscles that are right now they are testing with pneumatics, but their plan is to use hydraulics
Got it.
with,
Okay.
with those muscles.
I think people are not taking world models super seriously yet in the robotics space. I think there are world model companies and there are robotics companies,
Mhm.
but um, in the same way that I saw that like humanoids was not mainstream 3 years ago. Even though lots of people talk about big game about world models, um, it is not the central kind of linchpin of many many AI companies today. Um,
Right.
for example, a frontier lab like Google doesn't use world models as the core of their AI system. Most of our robotics competitors, to my knowledge, don't work on a world model as their core AI system.
Right.
And for us, like we invested a lot in that, and it's not our policy yet, but I could see a path where that becomes more mainstream in the future. Just to throw out there, like what's sort of out there at the moment.
Right. Right. Right.
Yeah.
NVIDIA announced their version of a world model, but
Hmm.
I'm not sure it's action controllable.
I think their
Yes.
latest Cosmos Predict 2, I think does this. At least one of their models that they released has that. And
Okay.
yeah, my understanding is that the team there has started adding robotics data to try to make it more controllable for
I see.
actions. Yeah.
Cool. So thank you, Eric, for having me here. And it was a pleasure talking to you.
Devang, thanks for the opportunity to chat.
Thank you. Cheers.
Thanks.